hardware security modules. Now, hardware security modules play a pivotal role in safeguarding digital interactions. So join us for an enlightening panel discussion where we will dive into the challenges and opportunities in building trustworthy hardware security modules. So our esteemed panelists include Mr. Sasikumar Ganesan from Modular Open Source Identity Platform, Professor Udayan Ganguly from IIT Bombay, and Professor Chester Ribeiro from IIT Madras. Now, steering this engaging discussion will be Professor Biswabandan Panda from the CSC department at IIT Bombay. I request Professor Panda and the panelists to take their seats on the stage. So, Professor Biswabandan Panda is an assistant professor at the Computer Science and Engineering department of IIT Bombay. Prior to that, he was an assistant professor at IIT Kanpur. He is one of the recipients of Qualcomm and Google Faculty Award 2022. His research interests include computer architecture for performance and security.
So, very welcome to this panel on hardware security. So, as the title suggests, this will be one of the panels discussing hard stuff. So, let's get started. So, let me introduce the panel members. I'll make it quick. So, we have Chester, who is an associate professor at IIT Madras. Before joining IIT Madras, he was a postdoc researcher at Columbia University. He did his PhD in hardware security from IIT Kharagpur. And before that, he was at CDAC, Bangalore. His current area of research is operating system architecture and VLSI security. He's particularly interested in applying learning algorithms and formal methods to analyze the security of systems. So, welcome, Chester. Next, we have Sasikumar Ganesan, who has over 20 years of experience in building platforms, security platforms. He has been the security advisor for several large Government of India projects. Sasi is actively involved in building digital public infrastructure and advise on security for most of the government initiatives on Digital India. He actively supports the open source identity platform, MOSIP, and the platform aims to provide secure and privacy-enabled digital identity across the world. As a software architect, Sasi has architected large-scale platforms from identity, security analytics, and IoT device security. And some of his solutions have actually met the high-performance requirements along with the security guarantees. So, welcome, Sasi. And finally, we have Udayan Ganguly from IIT Bombay, who is a professor here in the W department at IITB. Prior to joining IITB, he was at flash memory application development at Sunnyvale, and his research interest includes resistance RAM, MOSFET architecture, neuromorphic algorithms, and circuit implementation. So, welcome. So, welcome again. I'll start with the hard question because it's a hardware security panel. So, the hard question is, what's the big deal about hardware security? Like, is this a real threat or just some news article, some media article creating a buzz about the security attacks that are coming into the hardware devices? So, maybe some initial comments from all of you.
So I think I'll start. So, first of all, it's wonderful to be here. It's an interesting topic because I think there's a lot of money riding on this, and that's a good place for us to start. So one of the answers to that question is that there is a lot of money riding on it. So clearly, somebody's interested in solving these problems, right? So what is my interest in this? I think there is a computer architecture piece, there's a software piece, and then there's the silicon piece. And I work at the devices level, which is when each of these transistors or these gates are sort of screaming out that here's the information, take it, right? So the question ends up being are we secure? And you have to secure at all levels because that's it's like a chain principle, right? So the government of India is really interested in this. That's a big thing. A lot of our national infrastructure is not protected to the extent that one would want to. Yeah, that I think will keep us busy for some time. So I think it's an interesting space to be in.
Sure. I think in all the cryptography that we spoke about, the most important part is securing the key, right? And how do you protect it? In the past, our protection was basically keeping it on a server in a safe place and using a password, which we thought is not hackable, and then we realized however complex your password gets, the faster you would hack. So for example, in 2008, when we used to advise people, we used to speak about probably 10,000 iterations of a hash with nuns together, you're better off. But today, 10,000 is nothing at the compute power at which you operate, right? Probably at a $60 or $70 Amazon compute, I could pretty much break most of the passwords. So you're now far more forced to find out how do I make this most important part of the cryptography, which is the algorithm is open. You have literally opened up how to actually encrypt, how to actually decrypt, or how to perform operation within it. But then the only important secret in this entire cryptography is your key and information about your key. So even a partial leakage of that information is good enough to derive a key. Whether the leakage happens at the hardware level, whether the leakage happens at the library that we are using, both could give you enough information about what's happening or what could possibly be the key, and then reduce the randomness to a smaller extent. So it's all about protecting that single piece of small information in the cryptographic world for us. That's all we're worried about. And all the money that we're speaking is about protecting that extremely small information.
Chester?
So if you look at hardware these days, right, modern hardware, and compare it maybe to what was present, say 30 years back, or 30, 40 years back with, say, the Intel 8086. So the 8086 had around like 30K transistors, or 30,000 transistors or so. And today's processors, the complexity is much, much more higher. So the number of transistors will be in billions, right? So we have software which is highly complex, but the hardware too is extremely complex as well. So just like we have software bugs, there could be bugs in the hardware as well, which can then, because it's right down at the bottom layer of your computing, a vulnerability or a bug in the hardware could essentially compromise your entire system. And there's nothing you can actually do about it, because most of your mitigations, your antivirus or whatever you're implementing, wherever you're storing your key, or even if it's in a trusted execution environment, eventually, if there's a bug in the hardware, everything is compromised. The second aspect is about how things, the manufacturing of hardware has actually changed over the years. In the previous years, like again, in the 70s or so, you would have these few companies, maybe the Intel, Bell, and labs like IBM and labs like that, which would essentially build the entire processor. They would do a large part of the operating system and so on. And everything is consolidated with these central players. But today, the game has changed. So you'd have like a large number of companies involved in the design of a single hardware, a single processor. You would have one, what we call as a system integrator, which would actually purchase these IPs from various manufacturers, integrate them into a single chip, use third-party EDA tools to compile them, and then finally fabricate it in a third-party house. So it's very easy for any one of these players in this entire flow to essentially modify just a little bit, add an intentional bug or an intentional backdoor into your hardware. And the problem is that when your chip essentially comes back after fabrication, all you have is this black box, this IC, where you can give the input and check whether the output is essentially correct. The detecting such backdoors in the hardware is extremely difficult, right? So whether, coming back to Bishwa's question, so whether this is a reality or whether it's a hype, there is no solid evidence to essentially show that there's been an attack based out of the hardware, but based on the complexity, based on how manufacturing is done, probabilistically, such an attack can essentially be possible. So I would essentially compare it with something like life on another planet. Statistically, we know that there are so many planets, and possibility of life somewhere else is quite significant. Is significant rather, and but we don't know of it as of yet, right? So with hardware attacks in practice, we have the same story. So I think it's a reality and something that we need to be concerned about.
Thanks everyone. So the first takeaway from this panel is don't trust your hardware. Okay. And now the next question is, if you don't trust your hardware, how do you build trustworthy systems? Because as Chester mentioned, right, so hardware is actually one of the base layer in your computing stack, right? So that's where the hardware security modules kick in. And with the current technology that we have in place, implementing different hardware security modules, what do you think? They are good enough for providing trustworthy, or the notion of trust from the hardware layer, or it's just a matter of time and someone will break them? Right? Maybe Chester.
Yeah. So yes. So like you mentioned, Vishwa, we cannot trust our hardware. But what we would really need to do is identify how much we need to trust the hardware, right? So there are wide ranges of applications. Some applications which are not very sensitive, but others maybe in a power plant or a nuclear plant which requires extreme security. So I would essentially say that you would require to quantify or qualify a particular hardware based on your application. So if you need your device or your hardware to be present in something very critical, you need much better security, right? So you need to focus on security over other things like performance or area. But you could actually relax this once your applications are do not have that much security requirements. For example, let's say something much lesser, like an IoT device, right, which arguably may require lesser security compared to, say, a critical sector. And in such a case, you could look at more other parameters, such as the energy of your device and so on, and adjust your security levels accordingly.
Sasi?
Sure. So to add up on what Kester said, right, when you're dealing with hardware security, it is not going to be just purely on hardware alone. There's going to be some level of software and layers of interactions that's going to work. So as much as we tend to think of hardware as a single part, most often the designs that you go drill down inside, you would look like multiple peripherals are actually interacting with each other. And they are anchoring within themselves. There are a lot of trust layers that are built. So I'm not sure how many of you tried to build a HSM. So I've tried my best to build a HSM myself. Still trying to make it better as we proceed. But one of the things that you'll realize is there is multiple peripherals that has to interact. And these interactions finally bring up to a certain state of nature where you could tell that you are in an active state or in a stable state. And only at that state, any cryptographic operations could potentially be safeguarded. Until then, nothing is quite well enough. So you have to actually attest every single peripheral that you're interacting with and make sure their state is to the expected state. So it's not just about figuring out, just do a secure boot and start it, but it is also about anchoring every root of trust that is within your device, which you need, and are they in the state at which you want them to operate, and they have to be verifiable and provable. Okay, that is one of the part of how you build that trust from the hardware layer. And again, as adding up on what said, your need for security differs in every single place. Right. So, for example, In the past, where the cloud world did not exist, the hardware security modules were built and operated in your data center, in your physical presence. It's quite a lot of time okay for you to think about, I'm not telling that's what I'm advising, but logically to think, leaking or a side channel leakage over an electrical signals is still better, or is it still okay and manageable, which means you can patch it a little later, compared to operating in a cloud where such leakages could actually, without your knowledge, could leak your information where you have no idea about what's happening behind the scenes. So where you operate then defines how much security you have to go through. And you think about the similar model on a USB token or a smart card that you're carrying, leaking electrical signals, which means 1.3 billion people with the tokens, there is not going to be a mass attack in the possibility. So when you look at the final threat vector and then drill down to see where and how you design systems, where do you compromise? Because you have to definitely compromise on something in order to make it economically viable to work. There is the highest scale just doesn't, at least I have not tried to build enough to make it confident about myself. But whatever you try, you have to economically also be viable in its sense only, then it works. So in that, the mass attack is a different one. So you have to also look at each of this hardware security, not in terms of blindfoldedly looking deeper. You should continuously keep looking at what is the threat vector that I'm trying to address and how much of that will influence. If a large mass attack happens, then maybe that's not the right direction to move. If a large mass attack cannot happen and it can be controlled well, and you have an opportunity to replace in a shorter run or a longer run, then you're better off to take that choice rather than drilling down into the other side of the world.
Then you want to add?
Yeah, I think this is a very good question. One of the questions is that, how do you know your hardware is secure? Right? Is there an objective metric for it? And the answer is that there is something called common criteria certification. So when we try to build a chip for, so one of the applications that we tried to do was to build a passport chip equivalent. Passport chips are something that are very important for the country. It comes from people like NXP, Infineon, and they are certified not in India. So, and there are about different levels of certification, EAL 1 to, I don't know, I think 4 to 6. 4 to 6. Yeah. Above 4 is that. Yeah. So 5.5 is like a passport, something like that, right? Yeah. And so there is a criterion for that, right? Now, the other question is, is there any lab in the country that provides that certification? And the answer is no. So, and that's a hardware certification. You have to sense the electrical leakage or, the electromagnetic leakage. And so that is one piece of the puzzle, right? The other piece is the design libraries. So suppose you want to build a hardware chip. At the gate level, are the gates guaranteed for non-leakage, right? And I don't think there is access to such what I call process design kits. So a digital engineer will have to use these to convert a RTL logic into a layout and then fabricate it, right? So if you look at the India position, which is not the international position, there is a serious asymmetry in what is available to us in the hardware space for us to actually implement some of these things. So I think the answer is that I think there's a lot of stuff that needs to be done, from preparing to create such technologies and to validation. And that knowledge difference has to happen at labs which are fairly physical. Now the threat vector stuff, if it's e-passport, I'm assuming that, a chip does have a significant implication if one of them or two of them are broken in some manner.
Okay, thanks everyone. So just to summarize and just to connect all the dots that we have discussed so far. So if you are thinking about making money in this sector of hardware security, then I think you should provide hardwares that guarantees different levels of security. And then you say, for few dollars, you can actually mitigate ABC kind of attack. You pay a few more dollars, now it's DEF, and then keep on getting more money, right? So that's the idea if someone is planning for a startup here. But yeah, on a serious note, it can't be a binary secure chip or secure hardware. It can be either dependent on the attack surface, where exactly the chip will be used, where exactly, or what are the users, who are the users, what are the capabilities. And finally, based on that, you can actually come up with a loose definition of security, which is practically secure. You may not give a guarantee that, okay, it is secure, but it is still good enough. No one can harm you, right? Okay, so moving on, now that we know that it's important to design secure models, so what exactly is the, what exactly is the way to go forward? Like, is there a mantra or is there an algorithm that everyone should follow? Or as Sasi mentioned, right, you build a root of trust and then create multiple, chain of trust, assuming that, everyone is actually respecting that trust, right? So is that the only way to design trustworthy hardware? So that's the question, yeah.
Yeah, so I would look at, like, there are two options that we could actually follow. So one is, like, go back to the old model and have everything, maybe from a nation perspective, everything done within the country. So that would involve, like the IPs, the hardware, the fabrication, and so on. And that's something I think as a nation we should definitely go for, especially when you are looking at highly sensitive hardware or hardware in critical applications. But the other aspect as well, where you want to essentially design hardware based on, say, open source IPs or import hardware and so on. So there should be one way of essentially identifying or standardizing this hardware. For this, unfortunately, we do not have sufficient tools. We have tools to, for instance, validate how much power a particular device is taking, whether it's functionally correct and so on, but not many tools to essentially tell you if there's a vulnerability in the hardware, right? So you for instance, design something in Verilog, and you need to identify whether, you need to determine whether there is possibly a hardware vulnerability, whether maybe the the power consumption from that device could possibly leak something from that hardware. So obtaining, or there's no tools as such today which can essentially perform this, right? So in the research, there is, of course, tools that are very recently being proposed, which could do a security analysis of the hardware. But commercially, I've not seen many of these. And of course, as we progress, then we would require some more stronger guarantees. We want to do essentially a formal verification of for hardware with respect to security. A third aspect is also to look at languages, right? So how you describe hardware so that you're able to essentially define constructs for security itself. So such languages, of course, it doesn't exist today, but these are like open research problems which are very interesting.
Sasi?
So my perspective about how do we go about is, I think we are not started yet. And that's a very depressing situation in reality for a country of millions of engineers out here, right? One of the reason why we don't do it, and practically, while at the hardware to the chip level, to the transistor level, I don't think many of us have a knowledge. But if you go in the industry today and actually deconstruct an HSM or hardware modules or your USB tokens, what you will realize is actually a lot of them do not have that knowledge. There are devices which have that, a lot of them do not have it. So I think we should not stop by thinking, okay, we don't have the transistor knowledge, let's gain that and then get it. No, I don't think That should be the way. Over the time, we may gain that knowledge. I think the way forward we should really look at it is a lot of these chip makers actually, again, buy the chip from chip or a wafer from somebody else. They don't actually do it themselves. All they do is they do a layering of chemical coating above it so that the EMP signals are weakened enough that you can't figure it out. They layer down these chips above one another so that there are metal coatings, there are chemical coatings through which you can actually reduce the risk to a better state. And that is how a lot of these devices being constructed today. And if that is the path forward, then that is actually a way we could all start thinking about how do we actually take a decent or a good enough chip that you understand to an extent. Maybe we could run through some of the professors or academic universities and then get through that stage. But the larger stage is about how, once I try to create something today, if I have to go through a compliance in the country or outside, because it is the common criteria or the compliance today, you have to really go out of the country and do it. And the costs are so humongous economically to be viable. The amount of time you would spend in building the hardware, you may be doing triple or 4 times the cost in order to even just get the compliance. And most often you're going to be rejected at least 5 to 6 times before even you can get to the stage. And it's approximately a 5-year timeline. That's a large timeline for startups to wait before knowing what's going to happen. So it is important that we start decreasing that timeline with the labs and with the way of putting out standards that is acceptable within this country. And for example, common criteria, I think India is part of this agreement that common criteria could be done in India and it will be accepted in any other country. So we could absolutely, at the political level, these are enabled for us to actually take it up. But the labs have not really come up because there is not much demand that's happening. But now with a lot of digital economy growing up, there is a huge demand for us to think about it. And provided we could make it, and make the common criteria even better than what it is, because a lot of times security is not about just what got done in the lab, but it is also about the supply chain. Because when you're going to operate in this black box that Uday was speaking, one of the biggest disadvantage you have is you don't know whether what you qualified in the lab is exactly what is produced. So it is also important to take this common criteria or FIPS or any other standard to the next level. Maybe we make a new standards, or we make new process wherein we don't just rely on labs to test from what I give them as a device, but is also go on the field, collect the devices on the field, go through the supply chain, and picks them up regularly at regular intervals and start validating so that you are not so scared about the black box to begin with, so that you at least have a way forward in moving this. And that would result in giving a confidence and giving the first basic trust to tell the lab has verified, and the lab will continue to verify over the time. As long as this chip is being sold, as long as this device is being sold in the market, there will be a lab which will pick up from the market and retest to make sure the security guarantee that they provided remains the same. Then you're trying to wade away some of this risk collectively together, because letting a startup or letting a company to just own that risk entirely is going to be a very difficult task. But if we could collectively, as a society, could bring down compliance and this as an ongoing process, probably it'll be a little more lesser risk for people to go and innovate in that space.
Udayan?
So I think, a couple of interesting things. So one of them is a root of trust, right? It's something very standardized and you have to build it, right? The other piece is, how does a semiconductor industry, which is so expensive, actually work? And the way it works is that unless you can sell 1 million+ pieces, you don't have viability. Right? So there has to be some level of, you can't do ASIC after ASIC after ASIC. You have to build a product that works for, say, 5 or 6 different applications in some manner or the other, right? So there is this consolidation of demand on one side, right? And some people have to do it. The other piece is the discovery piece, which is, how do you discover vulnerabilities? And that is not an open source public discourse position, right? For example, to pick up an electromagnetic signal, right? You can put in one probe and you can say, oh, look, I have got one channel and I'm getting information from one channel, right? What about if you put 1,000 probes? Does your process become different? Can we do it? And the answer is, if you look at a commercial technology, most of these magnetic field sensors are cryogenic sensors. They work on superconductivity. But recently, there are sensors which are room temperature based on quantum states, right? So there has to be some sort of an establishment-based approach on the discovery side, right? As to whether there's a threat or not. But on the other side, designing chips, I think that is not a big problem. There are standard modes by which other countries, other startups do it. And in the hardware scheme, I think recently there were about 3 companies which actually were acquired in the hardware space in India. All the people who were doing hardware were like doing high fives, because after 13 brutal years, they actually got acquired. And it was not a big sale, but it was the first proof point that, so Steredian got bought by Renesas, Serial was bought by Micron, Sankhya was bought by Tejas and Tatas. So 10 years is a given in hardware. Nobody worries about it, right? So I think that, there are these things to be done here. We just have to do it in a systematic manner.
Yeah. Okay, thanks. So pertinent points, right? Like we need an ecosystem where we also facilitate offensive research, where you break systems, right? Usually we try to mitigate or patch systems to, mitigate certain kinds of attack or design a secure system. But we also need people who can actually break the existing system and say that, wow, this is a new way of attacking your chip, even if you guarantee that it is secure, right? So it's a cat and mouse game, and I think that will continue at least for a few more years, if not decades, right? So hopefully we'll get some sort of metric or some sort of certification that says that, if you clarify or if you, clear this test, then it's kind of guaranteed that your hardware is secure, right? So yeah, my next question is similar to what Udayan just talked about. So how do you groom the next generation, our students, right, who can actually contribute to this field of hardware security, keeping both the offensive and defensive side of this hardware security? Because you can't teach hardware security in a way the way you used to teach, let's say, any conventional courses, right? This is a different piece altogether.
Yeah. So Biswa, I really like the question. Okay. I really like the question because this sort of goes back to the fundamentals of pedagogy, right?
Yeah.
There are these structured problems, power performance area for a chip.
Yeah.
Right? Or you take the equivalent in memory, like capacity, latency, right?
Yeah.
The problems are roughly, the measures are clear, and you play to that measure.
Yeah. So the trade-offs are also clear.
Right.
Yeah.
And of course, some interesting people do an interesting, breakthrough, and that changes the system. But on the average, people can survive by, say, like a Moore's law. Every 2 years, you chuck out a chip. It's a lot of work, very interesting work, but there is an end goal, and it's all very structured, right? Goes back to, how we teach stuff, right? And what sort of people are going to be interested in this cat and mouse game. They are not the average set of people who would just, say, will I get my reward now, right?
Obviously.
It has to be people who are looking for some sort of an adventure. But I am assuming that, in this ecosystem, there are 2%, 3% guys who are interested, and we don't. India is a game of numbers, right? I mean, we still shake a bunch of people, 2% we get. So I think we're okay.
Okay. Any other comments?
Yeah, I think we should let people know that it's not going to be a difficult one, and get the regulation to actually help them better is my perspective, because the fear of, so suppose you make something very, very good and very nice, right? I remember about probably 8 years or 10 years before, if you could make a POS terminal, there was no lab which could actually certify you here. You had to either go to Singapore or you had to go fly down to Europe somewhere to actually get it certified. And that actually did not let much companies from here to actually compete. But today, if you see, there are quite a lot of interesting way of POS terminals that have come up in our countries. I think we did overcome that situation very well enough. But instead of making that battle very difficult, because POS terminals are a little more like 1 year or 2 year kind of a time period, but HSM kind of a device are like 5 year time periods. So if we could make regulatory help or use those political nature that our common criteria, we could have the labs, even government could set up labs. It may be little more easier for a lot of the researchers to come down and sit in whatever, it's Delhi, Bangalore, or Mumbai, or wherever it is, to sit and do the work and get this more understanding, because more people walk through the compliance, the more understanding that you get and the more knowledge that we gain. And that is a continuous exercise, right? First 3, you check them out, find the ways to get them geared up and do that. Now you're internationally eligible to sell anywhere. Now the market is wide open moment you do this. And that even provides a good economic opportunity for a lot of us to get in and dig through that space. Otherwise, 10-year time period with not knowing whether you'll be successful or not, with zero knowledge about how the compliance works anywhere else, and what's the chance of rejection, and how long is the rejection, is all a difficult exercise today.
Okay, Chester.
Yeah. So with the with India's initiative in the semiconductor space, right? So we do need people who also understand the hardware, the security aspects when you're dealing with semiconductors. And for that, you actually require a lot of students, or we need to at least train a lot of students who can actually at least understand what security is at the lowest level. Now, this has a lot of challenges. For instance, unlike software security, right, where you could actually have CTFs and stuff like that, when you're working with hardware and the security aspects of hardware, you require equipment. You may require oscilloscopes, and not your oscilloscope which you may find in a typical college. You'd require one which may be like at least like 10 to 20 lakhs, and that's the lower bound of it. And this would be the minimum cost to essentially get started on hardware security. So the challenge would be to essentially get this equipment and get students to be able to access these resources remotely. Yeah, so one experiment we were actually doing at IIT Madras is where we have such a setup, and we wanted to see if we could make it accessible remotely over the network or through a cloud or something like that, so that somebody or student who's actually interested could essentially log in, download a code into a processor, conduct a side channel attack, for instance, on that code, and essentially learn the way of how a side channel attack would essentially work. Right. Another aspect is a bit more challenging, but there could be CTFs specifically focused on hardware. So from IIT Madras, we had this embedded CTF last year, which was at a nation level, but a lot of it was done online. But last phase, we actually got the finalists to IIT Madras, and they had to work hands-on with boards. So if we could facilitate this, find ways which you could have teams accessing hardware, accessing resources which are available, I think that would essentially help, right? Globally also there are contests like, there's one called Hack at DAC and Seesaw, which both, I think one is from Texas, I think A&M, yeah, and the other one is from NYU. So this essentially kind of fosters hardware security. And there are a lot of teams from Europe and US, but fortunately from India, there are hardly a handful of teams which actually participate in this. I hope that this essentially changes over the next couple of years.
Thanks, Chester. Maybe in the interest of time, we can take few questions from audience. Yeah, Sridhar.
Thank you very much for a very stimulating panel. So my question is like this. The good news is that the problem has been formulated. The good news is also that we already know there are companies like Tejas who have solved it in a vertical slice. The good news is also that the powers that be in the country are very alive to the situation. So the question is that if you look at how things have progressed, be it in the industry abroad or even local software industry, there are some catalysts which are there, which get the action started in multiple places. I can quote the example of NASCOM, for example. Or in the product space, I can quote the example of Icepert. Are there similar agents here in the country? Any comments about that and what can be done in that direction? Because the student problem will get solved very quickly if the overall ecosystem is activated to solve the problems like expensive oscilloscopes or lack of tools.
Sasi, you want to take that?
Yeah, that's going to be a tough question for me. At least I have not encountered any project or any. There are IoT labs, for example. There are so many IoT labs where you could go and test, build. There are open lathes that are available in Bangalore and other places where you could go and structure and do a lathe work and then get things done. But I have not, at least, this was the first time I heard IIT Madras having something like that. But accessibility to those devices is a must in order to help. But what would be the one which will push that path is about applications. Where are the applications that really need these kind of devices in our market space? As I said, right now we're getting into the digital economy. There may be a need for it. But unfortunately, with secure confidential computing, one of the biggest problems that I have with that specific space is the fact that it is going to be only the big players. There's never going to be a small player entertained within that space, and unfortunately that's going to push down any possibility of anybody, because either you have to be a cloud compute provider in order to make that kind of a scale, or we open up that space and move it into the open source. For example, there's a good work that Open Compute Project is doing. I don't know how many of you have looked through this space. There are two interesting work that they're doing. One is to open up that space to an extent where how do you let somebody else build a new chip, completely new different ways, and still get the attestation and guarantee on that. That's one space that they are in. The second space is about secure boot and how do we actually collaboratively make a secure system up to an extent where it is operatable, right? One at the hardware level and one at this. So this level, they've done a pretty good job. The other one seems to be lagging, but there seems to be a collective effort that we need. I find a lot of very less participation there as well, or maybe promoting those standards within our country to make things viable, or trying to push in an economy where only those certified or those who compliant to those kind of open ones could actually participate, then gives us an entry door to, or any startup players an entry door to actually get in and start doing something useful. Those are ways of possibly bringing up, right, labs and this together has to cooperate to make that work. At least that's what
So I had a pretty interesting experience. So we tried to put together a story because we developed this security chip piece. So we could manufacture it inside India, the physically unclonable function. There's a 180 nanometer lab at Chandigarh, and the way I realized is that anything big, the government really asks for guarantee of success, right? So if there is no, and so it's hard for them to even do a pilot. And some of the problems in this space is that, if it's an established field, where, what we said, it's a microprocessor development, the give and the get are very clear. Government can support it because they have done equivalent things before. Something where it requires some new space of, having some computer science, encryption, math, chip design, people who are trying to break the chip. This sort of a connection to appear is not an easy thing. And I think I'll be remiss if I did not plug in for the center that I am part of now. So this is Semiconductor Center. So since you talked about semiconductors, I thought that I'll jump in at the moment. So, there's a Semiconductor Center at IIT Bombay. It's a center for semiconductor technologies. There is a circuits and systems piece. There's a materials piece. There is an IIT Bombay microprocessor, just like IIT Madras. There's a Navic chip. So it's not that it doesn't exist. There also exists people like Dipdeep in Kharagpur who do something. But to bring them together is an unlikely event that has to be catalyzed, and something interesting comes out, or you make the right connections. I think it's about the right connections. Something is possible, but it's not a natural thing that will happen. So,
maybe in the interest of time, one last question. Yeah.
Hello, I'm Nishkarsh. I'm a first year MS student, and my question is to Professor Chester. You said a statement about formal verifications about hardware systems, like you do some formal verifications about whether they are secure or not. So just if you could explain, like, what are the methods, what do you do on formal verification for the
Okay, so that's an excellent question, and if you're starting your research, that's a very good thing to actually look at. Formal verification at the hardware, specifically for security, is, I would say, quite at its infancy. I would not look beyond like 3 years of papers in conferences which actually talk about this. I don't know too much of it either, but just quoting some of the papers that I have read, specifically in the aspect of microarchitectural attacks. So there has been work which can prove that your processor, given your RTL, or given your Verilog code or your system Verilog code of your processor, does not leak information or does not leak side channel information, and this can be proven based on some specifications which are essentially written, right? So this being said, again, it's relatively a new topic, but there's a lot of active research going in this direction.
So just to add a data point, so formal methods or formal verification is an interesting idea to pursue if you are considering hardware security or architecture security. The problem that I have seen, at least from last few years at top architecture conferences, is the model will work based on the specification. And in most of the cases, you don't have a precise specification, right? Or even if you have a specification, you don't know whether the hardware respects that specification, right? So for example, if you want to make a claim that my Intel processor is secure or AMD processor is secure, you don't know how exactly they behave. So your specification is limited based on your knowledge. You don't know how exactly they are implemented, right? But yeah, just to say, it's a pretty interesting topic to jump into. Thanks again. Thanks to all the panel members.
A big round of applause for our panelists. So thank you all for joining this session. Now I would like to invite Dr. Sridhar Shukla to please join us on stage and felicitate our panelists. So we thank Professor Chester, Mr. Sasikumar, Professor Ganguly. We also thank our moderator, Professor Biswabandan Panda.